Is there life beyond Earth? This is a question that resonates deep within the human spirit. You know, it's a query that has echoed through millennia, whispered around campfires and debated in the grand halls of philosophy and science. It matters because the answer, whatever it may be, fundamentally reframes our place in the cosmos. Knowing we are not alone would be a profound revelation, altering our perspective on biology, culture, and our own significance. Conversely, discovering that life is a singular earthly phenomenon would grant our planet a preciousness we can scarcely imagine. The search for this answer is not a single event, but a long, unfolding story, a timeline of human curiosity and ingenuity, stretching from ancient dreams to the sophisticated scientific instruments of today. This journey is a testament to our relentless drive to explore the unknown. Long before the advent of telescopes and spacecraft, humanity looked to the night sky with a sense of wonder and awe. People across countless cultures watched the steady march of the stars, the wandering paths of the planets. They wove these celestial bodies into their mythologies, cosmologies, often imagining them as other worlds, the homes of gods. These early ideas were not scientific in the modern sense. They were born from imagination, philosophy, and the desire to understand. Thinkers in ancient Greece, like Epicurus and his followers, argued an infinite universe with infinite worlds, some surely inhabited. Powerful, speculative leaps, not observations. These dreams were seeds from which structured inquiry would grow, establishing that Earth might not be unique. For centuries, this perspective was overshadowed by geocentrism, placing Earth at the center of creation. The heavens were perfect and unchanging, unlike the mortal world. Worlds teeming with life challenged this order. Stars were ethereal lights. Planets wandered around us. The cosmos was for us, not for others. The transition from speculation to early science was gradual, beginning with measurement and mathematics applied to the heavens. Astronomers in Babylon, Egypt, and Greece tracked planetary motions with increasing precision, developing models to predict eclipses and alignments. Though cosmologies were flawed, their empirical records laid groundwork for a new approach. A shift from telling stories to decoding mechanics set the stage for revolution. Persistent orbital anomalies were cracks in geocentrism. It would take new tools and new thinking to open those cracks. Early scientists mapped a small island of knowledge, unaware of the ocean beyond. The 17th century heralded a monumental shift, opening the door to the modern search for life. When Galileo pointed his telescope skyward, he shattered the old cosmos. He saw mountains and craters on the moon, revealing it to be a world of rock and shadow. He discovered moons orbiting Jupiter, proving not everything revolved around Earth. Evidence mounted for Copernicus's sun-centered model. Earth lost its privileged place. It was just another planet. This revolution reshaped the question of alien life. If Jupiter had moons, could other stars have planets? The universe felt larger and filled with potential. Christian Huygens reasoned the stars were distant suns, likely with planets. A plurality of worlds returned on firmer footing. Speculation became grounded in physics and astronomy. The universe was no enclosed stage, but a vast arena of countless suns and worlds. Data were limited. Life on Mars or the Moon remained untested possibilities. Inquiry turned inward. Microbes discovered. Chemistry and biology unraveled life's building blocks. Living things are made of common elements and require liquid water and an energy source. This became a new filter for the search. The question evolved, not just is there life, but where do conditions exist for life as we know it? The dawn of the space age transformed passive observation into active exploration. We could finally travel to the worlds once glimpsed through telescopes. Robotic emissaries became our eyes, ears, and hands. First close-ups were exhilarating and sobering. Alien, often hostile. Lush visions faded to harsher realities. But these were crucial first steps. Data to ask better questions. Viking 1976. The first and only missions to explicitly test for active Martian microbes. Results were tantalizing yet ambiguous, likely unusual soil chemistry. Lesson learned. Searching for life is hard. We needed deeper context, environment, geology, history. So exploration shifted to follow the water. Ancient rivers on Mars, hidden oceans on distant moons. Ingredients are common, organics in meteorites, on comets, and in giant planet atmospheres. Evidence of past water on Mars and widespread present-day ice. We haven't found life yet, but many places could be, or were, habitable. Our solar system is now a natural laboratory for origins and habitability. Mars holds a special place for compelling scientific reasons. It's the most Earth-like planet, similar day length and seasons, but today it's cold, dry, thin-aired, irradiated. Rocks tell of a warmer, wetter past. Dry deltas, lake beds, water-formed minerals. Conditions for life may have existed. Today's Mars question: did life ever take hold, and are traces preserved? Rovers hunt biosignatures and cache samples for return. What about life today? Underground refuges, shielded, stable, briny pockets are plausible but hard to probe. So far, intriguing clues, no smoking gun. Complex organics found, the building blocks of life, yet also made abiotically. Seasonal methane, biological on Earth, but geology can produce it too. Each clue is a piece of a larger puzzle. We have not found life on Mars, but we have confirmed it was once habitable. Returned samples may finally answer whether life's spark ever ignited there. Beyond Mars, exciting prospects lie around Jupiter and Saturn, moons encased in ice once thought inert. But Galileo and Cassini flipped that view, strong evidence for global subsurface oceans. Europa and Enceladus may hold more water than all Earth's oceans combined. Key ingredients present: water, energy, chemistry. First, liquid water. Second, energy. Tidal forces need interiors, generating heat in darkness. Vents could power ecosystems independent of sunlight, just like Earth's black smokers. Third, chemistry. Oceans likely rich in salts and organics. Europa's ocean may meet rock, fueling complex reactions. Enceladus sprays water into space. Cassini sampled the plumes. It found water vapor, ice particles, salts, silica dust, hinting hydrothermal activity, complex organics, and methane. These finds broaden habitability. Life might thrive in cold, dark oceans powered by tides and geochemistry. Europa Clipper will probe ice and chemistry. One day, a lander or cryobot may reach the ocean, an epic quest. For most of human history, our planets were the only ones we knew, until the 1990s. Discovery opened the floodgates. Ingenious methods found planets rapidly. Kepler revolutionized the field, staring for years, catching tiny dimmings from transits. Over 5,000 confirmed. Planets are common. Most stars likely host planets. Hundreds of billions of worlds in the Milky Way alone. A staggering variety, including Earth-sized planets in temperate zones. Habitability needs more than distance. Right atmosphere, long-lived star, climate regulation. Many will still be barren rocks. The search is now galactic. Challenge. Move from detection to characterization. We must find which worlds are rock and water and which have friendly atmospheres. How do you study a planet light years away? We cannot send probes. Our only tool is light. By collecting faint light, we can tease out remarkable information. Transit spectroscopy analyzes starlight passing through a planet's atmospheric limb. Breaking light into colors reveals chemical fingerprints. We search for biosignatures, gases or combinations suggestive of life. Earth's oxygen comes from billions of years of photosynthesis by plants and microbes. Methane, quickly destroyed by oxygen, is replenished by life. Detecting oxygen and methane together would be powerful, though not definitive. Nature is clever. Geology and photochemistry can mimic life. Care is essential. We'll likely need a suite of gases out of chemical equilibrium, a pattern hard to explain without a biosphere. This is where powerful new instruments like the James Webb Space Telescope are game changers. With a massive mirror and infrared finesse, JWST captures faint atmospheric light of small worlds around cool stars. It can detect water vapor, carbon dioxide, methane, and other key molecules. JWST alone may not confirm life, but it begins the chemical census of potentially habitable worlds. We're moving from discovery to diagnosis. Next-generation giants, on the ground and in space, build on Hubble and JWST. They'll analyze Earth-like planets around Sun-like stars. They'll hunt oxygen, methane, the glint of liquid water, even seasonal shifts. The aim: move from hints to multiple cross-checked lines of evidence. It's a marathon: patience, rigor, humility, and every claim tested against non-biological explanations. We stand at a remarkable crossroads. No definitive evidence of life beyond Earth, yet a universe rich in habitable real estate, promising solar system targets, past Mars riverbeds, hidden oceans of Europa and Enceladus. Across the galaxy, billions of temperate zone worlds. We have a clear scientific roadmap. Next steps: bigger, better tools. Return pristine Martian samples to Earth's best labs. Orbiters now, landers later. Analyze plumes and one day reach hidden oceans, demanding decade-scale missions. But they offer ground truth. In seeking others, we learn about ourselves, Earth's origins, and the fragile conditions for life. We don't have the answer yet, but we have a plan, the tools, and a cosmos of possibilities. The search continues, driven by cautious hope and scientific curiosity.